What's up guys, it's me Sir Ernest, and today we will have our experiment number 3 entitled Resistors in Series and Parallel. So in order to understand our experiment, let's have a short lecture on this topic. To start with, let's look at, for example, uh, a single loop circuit. So here what we have is a single loop circuit where we have a battery connected to a resistor in a single loop. Okay, so here we have a single loop circuit with resistance R, and that is connected with an ideal battery. So here the operative word here is your ideal battery. So that means your battery doesn't have any internal resistances. So therefore, the resulting current throughout the circuit is the same. And this is by conservation of charge. The EMF on the battery is defined as the energy per unit charge transferred to the moving charges in a battery. So because of the closed circuit, or because of the single loop, and there's a potential difference between the terminals on the battery, there is now what we call an electric field. And because this battery contains an EMF, which is the energy per unit time, and we are considering an ideal battery, so that means the quantity IR by Ohm's law is the energy transferred per unit charge from the moving charges to the thermal energy within the resistors. Because we have an ideal battery, all the energy that is contained in the battery can be transferred to your resistor. And by Ohm's law, that EMF is equal to the product of the current through the circuit times the resistor at the resistance of the circuit. Or current is equal to the EMF provided by the battery divided by the resistance in a single loop circuit. Now, what happens if we have a series of resistors? So we say we have resistors connected in series. That means the resistors are connected one after another. So for example, we have our first resistor, let's call it R1. So one terminal of that resistor is connected to one of the terminals of the battery, and the other terminal of your resistor is connected to one terminal of another resistor, and so on and so forth. So for the third and last resistor in this example, what we have is this end of R3, we call this the third resistance, or R3, is connected to the other end of the battery. So in this case, we have a single loop circuit containing a battery and 3 resistors. Now we can actually combine these resistors into one single resistor. We call it the R equivalent. And how do we get that equivalent resistance? Okay, so by conservation of charge, when the potential difference V is applied across these two terminals A and B, okay, the resistances for each in this circuit will have identical currents. So that means whatever current that is passing through this point, or this line, or this resistor, is the same current that will pass through this resistor and will pass through resistor. Let's call those currents I1, I2, and I3. So in this case, we have the total resistance within that single loop circuit, or a single loop circuit with 3 resistors. So this is total, and this is equal to the current flowing through R1, the current flowing through R2, the current flowing through R3. And if we have n resistances, that is also equal if we have a resistances connected in series. Now, by conservation of energy, because you only have one source of energy, So that means this energy can now be distributed throughout R1, R2, and R3. So in other words, the energy coming or the EMF provided by your battery, which is the same as the voltage across AB. So this is the voltage across these 2 points. So the total energy that is provided will be divided by R1, R2, and R3. So specifically, the sum of the voltages across R1, V1, the voltage across R2, V2, and the voltage across R3, V3, etc. If you sum them, that should be equal to the potential difference or to the voltage provided by your ideal battery. Okay, now remember that for Ohm's law, the voltage across a resistance or across a resistor is equal to IR. So what does it mean? If you're going to substitute this here, so this becomes I1 R1 plus I2 R2 plus I3 R3, etc. up to IN Rn. And because I1 is the same as I2 and it's the same as I3, and that's the same for IN, this is equal to the total current flowing through the circuit I times the equivalent resistance. So because I is equal to all the currents here, so therefore the equivalent resistance will now be equal to the sum of the resistances of all the resistors within that loop. So in this case, R1, R2, and R3 are connected in series, so that means the equivalent resistance Req would be equal to R1 plus R2 plus R3. So in other words, the resistances connected in series can be placed with an equivalent resistance R1 that has the same current I and that same total potential difference as the actual resistances. Okay, so that is for a single loop circuit containing resistors in series. Now what happens now if we have a multi-loop circuit? So in this case, we call our resistors to be connected in parallel. So when in this case, okay, because remember that the potential difference applied by the battery on AB would be the same here, would be the same here, and everywhere in between. Because this line, including this line, and this line, are actually equipotential lines. Same goes here. So that means, okay, the potential energy provided by the battery between AB would be the same as the potential difference across R1, across R2, and across R3. So that's the what we call the difference between resistors in parallel and resistors in circuit. So R1 here, R2 and R3 they have a common point A and common point B. So in other words, the potential difference on AB, which is provided by the battery, would be the potential across R1 would be equal to the potential difference across R2 and R3 up to Vn. Now, what happens now if we're going to consider that current I? As you will notice here, that the current that will flow from this positive terminal from the battery, I, when it encounters a junction, so we call this a junction. Okay, so what happens there is that this current will be divided into two. I1, and we call that I1 as the current flowing through R2, and the rest will be the current flowing through I2 here plus I3, so that when this current encounters another junction, this will be split into I2 and I3 here. So when I1, I2, and I3 pass through their corresponding resistors R1, R2, and R3 respectively, so these three currents will recombine here at AB, producing the original current I. And that is because of the concept of conservation of charge. So by conservation of charge, the sum of currents I entering any junction must be equal to the sum of the currents leaving the junction. So all in all, if I is the total current in the circuit, that is equal to the current flowing through R1 plus current flowing through R2 plus current flowing through R3, etc. And again, by Ohm's law, V equals IR, or I is equal to V over R. So in this case, if I is a total current flowing in the circuit, as if this circuit is equivalent to a single loop circuit with one resistor and one battery, these are equivalent compared to E. So this is E over R, or sometimes this is V AB over R, equivalent. And this is equal to what? This is equal to V1. V1 is the voltage across R1 divided by the resistance of R1 plus V2 over R2 plus V3 over R3, etc. Because remember that V1 is equal to V2 is equal to V3, etc. So that means we can cancel all the V's, including the E. So the end result is that we have 1 over R equivalent, and that is equal to the sum of the reciprocals of the resistances of each resistor connected in parallel. Okay? So sometimes what we do there is R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc. And then we take the reciprocal. Okay? So resistances connected in parallel can be replaced with an equivalent resistance RQ, and that has the same potential difference V and the same total current I as the actual resistances. Now in this experiment, you're going to do 4 circuits. The first two circuits will correspond to your series circuits and to your parallel circuit. But the second two circuits, you're going to consider a combination of series and parallel. So let's have one example. Okay, so in this case, we're going to look into circuit analysis, wherein we were going to find the equivalent R, or R equivalent. So let's consider this circuit. So here we have a circuit consists of 4 resistors. These resistors have the following resistances. One has a 400 ohm resistor, one has a 560 ohm resistor, a 600 ohm resistor, and an 800 ohm resistor. And these are connected in this manner, and this is connected to a 12 volt battery. So one thing that you should know here is that we can label the terminals of your components. Okay. So in this case, if we're going to have this circuit, which is a combination of series and parallel, so what we're going to do is we're going to break down the circuit by starting with the innermost combination of the entire circuit. And when we analyze this here, we have the following. So for example, this is actually connected. This terminal of the 800 ohm resistor is connected here and is connected here. Okay, so by parallel, so this part is parallel to each other. However, this part of the 800 resistor is not in common with this part and in this part. So that means this resistor and this resistor are not in parallel and they are not in series. Okay, same goes with these three. However, if we're going to consider these two resistors, this and this and this are both common for the two resistors. So that means this is the this is the first part of the circuit that we're going to reduce. So in this case, we're going to reduce this parallel combination, and we're going to use this calculation to compute for this equivalent resistance. In other words, this resistor, this 240 ohm resistor, by using this computation, is equivalent to the combination of this resistor and this resistor in parallel. Hence, this equation. Okay, again, these two resistors are in parallel and their equivalent resistance is computed by this equation, and the result is 200 ohms. Okay, so now we have break down the circuit first level. Now, as you will notice here, this is not in series here and it's not series here. However, these two resistors are in series with each other. So that means that is the second combination that we're going to use or to break down in order to make our circuit simpler. Okay, so we're going to reduce this series combination to produce an equivalent resistance. So this combination of the 240 ohm resistor and the 560 resistor, by combining them by this equation, we end up an equivalent resistor with a resistance 800 ohms. Okay, so as you will notice that these two resistors are now in parallel to each other, and that is the last step in this breakdown or circuit analysis, wherein we're going to reduce this parallel combination and then produce a single resistor with a value of 400 ohm. Remember that these two resistors are in parallel, so we use this equation to compute for this resistor. And because our circuit is now a simple circuit containing one resistor and one battery, we now have we can now consider this as our equivalent resistance. Okay, so the equivalent resistance of this combination of resistors is 400 ohm. And as mentioned earlier, because the equivalent resistance of this circuit is 400 ohms, we can now compute the total current flowing through the circuit by Ohm's law, wherein I is equal to V over R, and the result is 0.03 amperes or 30 milliamperes. Okay, so again, when you're going to analyze a circuit, you start with the innermost combination of the entire circuit. So in this case, as a review, we started with the reduction of this parallel combination, making this equivalent resistor, and this resistor is now in series with this resistor, and therefore we combine them as a series combination, producing this resistor, and then this and this resistor are both parallel to each other, thereby producing this equivalent resistor. Okay, now if you want to know the current and the voltages for all these for the original resistors as well as your intermediate resistors, what we do is we start with the equivalent with this circuit, and then we go backwards like this. Okay, however, this is for this experiment, we're not going to do this, so but this is for your reference only, so that this will be able to help you with your lecture in due time. Okay, so what happens here is that from your simplest part of the circuit or simplest version of the circuit, you try to rebuild the circuit, okay, following the relationships between your resistors until you arrive at your until you arrive at your original circuit. In this case, you will be able to calculate the voltage across each resistor in this circuit, as well as the current along the resistors. Okay, so that's it. So in your experiment, you're going to do the last two circuits, wherein those last two circuits are combination of series and parallel. So in short, in this experiment, you should be able to determine the total current flowing through a series circuit and parallel circuit, and determine the voltage across each resistors in a series circuit and parallel circuit. And you're only going to need one material here, which is an online and offline version of Circuit Construction Kit for a DC Virtual Lab from PHYS Interactive Simulations, available at this URL. Okay, so in the next video, we're going to look into the actual experiment. In the meantime, I hope you learned something today, and I'll see you guys in the next video. Bye-bye.